Assalamu alaikum. Good afternoon, everyone. We are in this block 3. Last week, we discussed the properties of the waves and the types of the waves. Today's topic is about the sound. First, the nature of the sound and how sound is produced. Sound is produced by vibration. Like when anything is vibrating to and fro, it produces sound. So example, and how sound travel through a medium. It travel through a medium by compression and rarefaction. So example, these are the air particles in the atmosphere. So these are the air particles moving randomly in the atmosphere. And you have a stick. If you move this stick to and fro, if you vibrate this stick to and fro, what you cause a vibration to the particle. The air particle will also vibrate. And this vibration travel from one place to another by compression and rarefaction. Compression means there will be region where the particles will be closer to each other, and rarefaction means the region where the particles will be away from each other. And this kind of wave, sound wave, is so production of the sound. How sound is produced? Sound is produced by vibration. Whenever anything is vibrating, it will produce sound. And how sound travel through a medium? From one place to another. So sound travel from one place to another by series of compression and rarefaction. Compression means the particles will be closer to each other, and rarefaction means the particle will be away from each other. And the compression, the particles are closer, so pressure will be high. Rarefaction, the particle will be away and the pressure will be low. And nature, sound is longitudinal. So what's the meaning of longitudinal? It means the direction of the motion of the particle parallel to direction of the wave. So the direction in which the wave travel and the particles are moving, they're in the same direction. That's why we call that as longitudinal. Example, as you can see in the next picture. See, this is a cone of a loudspeaker. So when we disturb, when this cone start to vibrate, you can see it is pushing the air particles, and these air particles travel from one vibrating in same as the direction of the wave. And there are regions where the particles are closer to each other. So region where the particles are closer to each other, this whole region is known as compression. And the region where the particles are away from each other and the pressure is low, we call that as rarefaction. And the direction of the wave is towards right, and the direction of the particle is right and left. So you can see when direction of the wave and direction of the particle is parallel to each other, we call that as longitudinal wave. Is it clear? The production of the sound and the nature of the sound. So sound is longitudinal and the vibration is parallel to the direction of the wave. But for example, you have a stick and you're vibrating to and fro. Sorry. So you have a stick and you're vibrating this stick to and fro. And a person is standing at position A, but the person at position, because whenever something vibrate, it produces sound. So a person is at position A, but he's not able to hear the sound. So what might be the reason why a person at not able to hear the sound? There might be two reasons. Number one, maybe sound is not in audible range. There is a range of the frequency for which our ear is sensitive, and that range is from 20 hertz to 20,000 hertz or 20 kilohertz. So any sound which is produced within this frequency range, we are able to detect. But if a sound is less than 20 hertz or more than 20,000 hertz, we are not able to record that sound. So maybe a person at position A is not able to hear the sound. Maybe it's not in audible range. That might be one reason. The second reason, the amplitude of the sound is too low. So if amplitude of the sound is too small, that might be a reason that we are not able to hear. Like example, what is the amplitude? Amplitude of the sound, like example, because when the sound travels from one place to another, I'm representing sound waves in terms of transverse wave to explain the idea of amplitude. So its amplitude decreases. So if a person is producing a sound at position 1, but what happened when the sound travel, its amplitude is decreasing. So maybe at position A, there is no sound received. Why? Because the amplitude might be too small. So these are the two reasons why a person is not able to hear a sound, even though a vibration produces a sound, but a person may not be able to hear that. Number one, maybe that's not in an audible range. What is the audible range for a normal human ear? It can record from 20 hertz to 20,000 hertz. This is the audible frequency range. If sound is more than that, we are not able to record. If a sound is less than that, if it's a vacuum, if we are considering there is air present, sound cannot travel through vacuum. So we are considering there is a medium present between the source and the observer, but still an observer is not able to detect a sound. So why a person is not able to detect a sound? Maybe there might be a vacuum, but because we assume that there is a medium, so that's why I did not say vacuum can be a valid reason here. So if there is a vacuum, then there will be no sound at all, because sound cannot travel through vacuum. Is it clear? So why a person may not be able to detect a sound? There might be two reasons. Third one is only if there is a vacuum, sound cannot travel through vacuum. So maybe a vacuum is there, you can consider. That's why a person is not able to detect a sound. So as a sound travel from one medium to another, travel from one place to another by compression and rarefaction. You can see the particles are closer, that's compression, and where the particles are away, that's known as rarefaction. And in terms of pressure, compression is a region of high pressure. So you can see the region where we have compression, we have high pressure, and the rarefaction, because the particles are away, so there is a low pressure. Another a source of a sound is there. This is also a longitudinal. Why a longitudinal? Because it is producing sound in all the direction. So sound is traveling towards left, right, upward, downward, and you can see the direction of the particle is same as the direction in which the energy transfer or the wave travel. That's why we call that as longitudinal. And regions are there where the particles are closer, that's compression, and the region where the particles are away, that's called rarefaction. Definition of the compression you have to learn. Compression is a region where the particles are close together and high pressure. Rarefaction is a region where particles are further apart and have a low pressure. Audible frequencies, the frequency which a normal human ear can detect, that range is from 20 hertz to 20,000 hertz. A sound below this 20 and above 20,000 are not audible, or ear cannot detect, a human ear, normal audible range. A simple experiment to show that the sound cannot travel through a sound required a medium, or sound cannot travel through a vacuum. So what we can do, we can use a vacuum pump here. We first a simple bell jar experiment. What is a bell jar experiment? There is a bell inside. Sorry. So there's a bell inside the jar, and we connect this to a vacuum pump. Initially, we have air, and we switch on the bell. When we switch on the bell, we are able to detect the sound. Why we are able to detect the sound? Because the sound can travel through air. So that's why we are able to receive the sound which is produced by this bell. Then what we will do, we will gradually remove this air out by using a pump. So when we remove this air out, what we will observe, we'll observe the intensity of the sound will decrease. The sound is getting lower, and eventually there is no sound at all. So if there is no sound at all, what it shows? It shows that because we created a perfect vacuum and no sound, it shows that the sound cannot travel through vacuum, or sound required a medium to travel. Is it clear? This is a simple bell jar experiment to know or to show that sound can not travel through vacuum. So you can see here the same experiment. A bell is there inside a bell jar and connected to a vacuum pump. As we remove the air out, the sound intensity will decrease, and eventually there is no sound at all, which shows that sound cannot travel through vacuum. If we want to compare the speed of the sound, example, we have solid, liquid, and gas. Which medium you think sound can travel faster? Which medium sound can travel much faster than the other? Solid, liquid, or gas? Sound travel fastest in solid compared to that of liquid, and in liquid it travel faster than gas. So sound travel fastest in solid. What's the reason why the sound travel fastest in solid? Because sound is by vibration of the particle in the same direction of the motion. In solid, the particles are tightly packed together. Sorry. Because in solid, the particles are tightly packed together. So if particles are tightly packed together, they can easily transfer the vibration from one place to another. Like when the first one vibrate, that causes second one to vibrate, that causes third one to vibrate, and so on. But where in gases, in liquids and gases, in liquids, particles are relatively far, and in gases, the particles are far away from each other. So that's why when we compare the speed of the sound travel fastest in solid. You have to learn these speeds. Speed of sound in solid, approximate speed is 5,000 meter per second. In liquid, it's about 1,500 meter per second. And in gases, it's about 330 or 340, or 300 is acceptable meter per second. This is approximate. Different gases, even the speed will be different, but on average, the speed is about 300 to 330. Now the experiment to find speed of the sound in air. So a simple experiment to find speed of the sound in air. So what we can do, we can do a simple experiment. Yes, what are the questions? Yes, what is the question? Sound can travel through gases. So even a balloon filled with hydrogen, a sound can travel. The speed will be different, but because it's a medium, so it can travel. The sound without a medium, because between the spaceships there's a vacuum. So through vacuum, it's not traveling. Sound cannot travel through a vacuum. Sound wave can travel from one medium to another. So sound can travel from solid to liquid, from liquid to solid. It can travel from one medium to another, but it cannot travel through vacuum. So experiment to find speed of a sound in air. If you want to find speed of a sound in air. So example, two persons, person at position A is having a starting pistol. What's this starting pistol? When he fires the shell, so two things will happen. It will produce light and it will produce sound. But because light is super fast, light travel very fast. The speed of the light is 300 million meters per second, which is too high. So when the person at position A fires the shell, so the light will instantly, the light will travel. As the light travel, the observer, when he see the light, he will start the timer. And when he hears the bang, so when he hears the bang, he will stop the timer, because that is the time taken by sound to travel from person A, observer A, to observer B. So they recorded the time, the distance. They can use a measuring tape and record the distance. To know the speed, speed is equals to distance divided by time. So distance we can measure by a measuring tape, and the time we recorded. A person, when a person at position A, he fires the shell, so both light and sound are produced. When a person at position B see the flash or the light, he will start the timer. When he hears the bang, he will stop the timer. So that is the approximate time taken by the sound to travel from position A to position B. So we have the time, can measure a distance by using a measuring tape, and distance divided by time, we will get the speed. Is it clear, this experiment to find speed of the sound?
Sir,
Yes.
I have one question.
Yes, Mohsen. Yes, Mohsen.
Sir, can you hear me?
Yes, I can hear you now.
Yeah, okay. So if the sound, like the waves, they will disintegrate or attenuate over time, over the distance, the further they move. But why does that happen? Like the reason?
Because what happened, the particles keep some of the energy It's like, because it's a transfer of energy. When a person at position A, he fires a shell, so example, that sound is also energy. So example, that was 100 joule. But as the particles are vibrating and transferring, so the particles keep the energy with them. They keep some of the energy. So as they keep some of the energy, that's why the intensity of the sound will decrease. It's not like the produce is 100 joule, but when the first particle collide, it may transfer say 98 joule. Then the second particle collide, it may transfer 95 joule. Then the third particle collide, it may transfer 93 joule. So the particles are keeping some of the energy, which increase the internal energy of the particle or the medium. That's why not the sound intensity always decreases as it travel from one place to another. Is it clear?
Yeah, okay. Clear.
So this is an experiment to find speed of a sound in air. So this, you will find this question, common question, like writing experiment to find speed of the sound in air. Look, when a person at position A, he fires a shell, two things happen. It produces light, that's one thing, and it produces sound. But when you compare the speed, of a light and speed of a sound, speed of a light is 300 million meters per second. This is a speed of a light in air, approximate. And what is the speed of the sound? It's only around 330. So you can see there's a big difference between the speed of the sound and the speed of the light. That's why when a person at position A, he fires the shell, within an instant, like a short time, you're able to see the flash or the light. And after some time, you will hear the bang. And this is very common. You can observe this difference, greater difference in the speed of the light and sound. If you are observing, say, a firecracker explode or any firework is there, so you will see that as the firecracker explode in air or the sky, so first you will see the light and then you will hear the bang. Why you're able to see the light first? Because within an instant, light is super fast, 300 million meter it can travel in 1 second, whereas sound only 330 meter per second. Yeah, that's also a reason. For example, if there is a thunderstorm and a lightning strike, so you will see the light first and then you hear the bang. Why the sound energy decreases? Because the particles in the atmosphere absorb sound. That's why, or they're keeping the energy, not transferring all of it to the neighbor. That's why the intensity or the energy of a sound at travel from one place to another decreases. So observer A and B are positioned at a known distance and record the distance D. Observer A fires a pistol and observer B sees a flash. He will start the timer, and when he hears a bang, he will stop the timer and repeat the experiment for accuracy and measure the distance between the observer A and observer B by using a measuring tape and distance divided by time, so we can find the speed. Echo means reflection of the sound is known as echo. So when the sound travel and it hits the surface and it bounces back, the reflection of the sound is simply known as echo. If the distance between the source and the reflecting surface is d, so the formula is speed is equals to the sound travel a distance d and return back distance d. So speed is 2d divided by t. This is whenever there's a reflection of the sound. And whenever we are using a reflection of the sound, there are two ways we can produce a wave. One is called a continuous wave. Continuous wave means continuously we are producing a wave. The sound waves are longitudinal, but I'm drawing a transverse to explain the idea, because transverse waves are easy to draw as compared to longitudinal. The sound wave will strike and it will bounce back. This is called a continuous wave. And the other one is known as the pulse. Pulse means a small signal, one wave or less than one wave. So we send a small wave, that wave will travel, hit the surface and bounce back. So to observe the echo or reflection, which one is suitable, continuous wave or a pulse? If you want to study the reflection, which one is convenient or easy to use, continuous wave or the pulse? To study the reflection, we prefer pulse. Why we prefer pulse? Why not a continuous wave? The reason for that, because when you're producing a continuous wave, you cannot distinguish, because what happened, the sound is traveling and the sound is coming back. So you're producing a sound and you're receiving a sound, so it will be difficult to detect the sound, like difficult to distinguish between the sound which is produced and the sound which you are receiving. That's why we do not use continuous wave, we use a pulse. Because when we use a pulse, we use one wave, that wave will travel, it will hit the surface, and when it returns, we will know that this is a wave which bounce back. So whenever we study the reflection of the sound or echo, we always prefer to use a pulse rather than a continuous wave. Why we prefer a pulse rather than a continuous wave? Because we can distinguish between the wave which is sent and the wave which is received when we are using a pulse. But if you are using a continuous wave, so in case of continuous wave, the sound which strike and the sound which bounce back, you are not able to distinguish between them or differentiate between them. That's why we do not use continuous wave. So the formula is speed is equals to 2d divided by t. What's the answer? To estimate the width of the valley, the climber start a stopwatch. He shouts and hears an echo from opposite side of the valley after 4 seconds. The speed you will take as 340. What's the answer? Yeah, what's the answer? it's a reflection. So speed is equals to 2d divided by t. So you need distance, you need this distance. So it will be speed multiplied by 2 divided by speed multiplied by time divided by 2. So speed is 340, time is 4 and divided by 2. So when you solve this, this will be 680 meters. Is it clear? Then what is the loudness? Loudness of a sound is refers to the amplitude. Like loudness of a sound is referring to the amplitude. If a sound is louder, it means it means it is having higher amplitude. Or in terms of compression and rarefaction, if a sound is louder, compression will be smaller and rarefaction will be larger. So if you want to represent, because sound waves are longitudinal, so when we represent like two sound waves are there, these lines are representing the place where the particles are present. So if the particles are closer, that is compression. And the particles are away, that's called rarefaction. Then again, there will be compression. Then rarefaction. So this is a compression, compression, rarefaction, rarefaction. So if we say a sound is louder, so what is the meaning of louder sound in terms of compression and rarefaction? Like when a person, example, is shouting. So what happened to the compression? The compression will come much closer to each other. Means the region, the particle will be very close to each other. And in a rarefaction, the particles will be away from each other. But because it is difficult to draw exact like the show in terms of compression and rarefaction, so normally instead of drawing the compression and rarefaction, what we simply use a transverse waves to explain the idea of the louder sound. Like example, no, the frequency, the number of the compression and rarefaction is not changing. That's why the frequency does not change. But like same number of compression and rarefaction, but the compression will be compact and rarefaction will be expanded. So instead of drawing a compression and rarefaction, how we represent a loudness? So if we say this is representing a sound wave. So if I want to draw a louder wave, so a louder wave means it, it will have higher amplitude. So this is how we represent the loudness in terms of transverse wave. Because it is difficult to draw the compression and rarefaction and show exactly. That's why, for the convenience, if we want to represent a sound is louder, like if this is one waveform, and the question is draw waves to represent a loud sound. So how you'll represent a loud sound? Means it will be higher amplitude. Is it clear? The concept of the loudness. The larger the amplitude, the more energy, therefore the louder the sound. So you can see 1, 2 and 2.5 waves. The first one is also 2.5 waves. The second one is also 2.5. 1, 2 and 2.5. But when you check the height, you will find height of the first one is smaller as compared to the second one. So it shows that it is louder or higher amplitude. The second property is refers to pitch. Pitch means number of vibration per second or the frequency. So if pitch increases, it means more compression and rarefaction. Or we can say higher frequency. So pitch affects the frequency. Higher pitch means more compression and rarefaction or more vibration per second. And to understand, if you try to say these words, bing and bong, which one you feel that you produce more vibration? When you pronounce the word bing and bong, which one you think you produce more vibration? When you pronounce the word more vibration. So practically, when you detect the number of vibration, when you pronounce bing, bing will produce more vibration as compared to bong. When you're saying bong, it's like you're not producing many vibrations. So to say a word bing, it's high frequency relatively. And to pronounce a word bong, you use low vibration, less vibration, or low pitch. So how many vibrations are there? Number of vibration in 1 second that is refers to pitch. And higher frequency means shorter wavelength or higher pitch. So you can see the first one 1.5, but for the second one 1, 2, 3 waves. So this is 1.5 hertz if it is in 1 second, and this one is 3 hertz because 3 waves in 1 second. Is it clear, the concept?
So your phone.
Is it clear? Any doubt in this part? Now, when the sound travel from one medium to another, it changes the speed. And we call that as refraction. So example, if a sound is traveling from solid to liquid, what happened to speed? Average speed, approximate speed of sound in solid is 5,000. In liquid, 1,500. Gases 330. So the speed of a sound decreases. So when travel from solid to liquid, the speed decreases. Then what happened to wavelength? If a speed decrease, the wavelength should also decrease because the frequency remain unchanged. The number of the vibration as the sound travel from one medium to another remain constant or does not change. So when the sound travel from solid to liquid or it travel from liquid to gas, so we'll observe the same change. Or travel from solid to gas, and opposite will happen if a sound travel from liquid to solid, gas to liquid, or gas to solid. We'll observe the speed increases, the wavelength increase, but the frequency remain unchanged. So frequency is a ratio between, so ratio between speed and the wavelength is called frequency. So frequency does not change as the sound travel from one medium to another. So moving from solid to liquid or liquid to gas, speed decreases, so wavelength also decreases, so ratio remain constant. Moving from liquid to solid, gas to liquid, or gas to solid, the speed increases, the wavelength also increases, but the frequency remain unchanged. Now some questions related to this sound topic. What's the answer for the first one? Everyone should participate, so it shows your understanding. Yeah, B is the right answer. The compression, the particles are closer, and refraction, the particles are away. Question 2. A sound wave has a certain amplitude. A second sound wave is quieter and low pitch. Quieter means that it refers to amplitude, and lower pitch means frequency. So D is the right answer. Question 3. I want participation from everyone. A is the right answer because it's mentioned it produces a louder note of higher pitch. So frequency should be higher and amplitude should also be greater. Question 4. A dolphin has a range of audible 150 hertz to 150 kilohertz, which can be heard by both human with good hearing and dolphins. The normal range for audible range for human, it's 20 hertz to 20,000 or 20 kilo. So D is the right answer because the lower limit is for the dolphin and the upper limit is for the human. Question 5. What's the answer? So reflection of the sound produce an echo. A sound wave travel from medium in one state into another cause the speed of the wave to change. Between which two medium it is traveling? Approximate speed in gas around 330, 340. In liquid it's 1500 and in solids it's about 5000. So it's 5000 moving from gas to solid. Question 7. Yeah, 7B is the right answer because the sound travel faster through solid. So that's why it will take a shortest time. Sounds are produced by vibrating objects at certain object vibrate, but a person nearby cannot hear any sound. Which statement could explain why nothing is heard? So why nothing is heard? Amplitude of, if amplitude is too high, then it should be heard by the person. So it cannot be A. Sound waves are transverse. That's totally wrong. Sound waves are long. The speed is faster, so a person is able to record it, but he's not able to record. Why? Because frequency of vibration might be too high. Maybe that's not in an audible range. We cannot detect after 20,000 hertz. We can detect from 20 to 20,000, not after, not not below. So B is the right answer. Yes, Mohsen, you have a question?
Serious. So in the solids and comparing travel of sound waves in solids, liquids, and gases, they then solids they travel faster, but they also travel short distances than others. So why does that happen?
Why it happened? Because the particles are keeping most of the energy within internal energy. Solids can, the particle can keep more internal energy. That's why. Like what happened basically, the particles vibrate, collide, and transfer energy. So because the spacing between the particle is so small, that's why within an instant they can transfer energy. But what happened, the amount of energy which is transfer is not same. Like it's a very small amount compared to what they take. That's why for a short distance it can travel.
So we can say that the solid particles offer the greatest resistance to the sound waves that travel.
Yeah, but the thing is, they offer they absorb greater amount of energy. You can mention
Yeah,
resistance, but if you mention resistance is higher, it means the speed should be slower. But practically, the process is faster, but not efficient.
yeah, yeah. Yeah. Thank you, sir.
Question 14. The diagram shows wave shape of two sound. The scales are same in each. How does sound 2 compare to sound 1? Pitch means number of vibration. Loudness means amplitude. Sound 2 is higher. If you say sound 2 is having higher pitch, it mean you can see how many waves, 1, 2, 2.5. How many waves, 1, 2, 3, 4, and 5. So this sound 1 is higher pitch, not sound 2. Or you can opposite, you can say sound 2 is having a lower pitch than sound 1. So D is the right answer. Question 18. So C is the right answer because sound waves are longitudinal and the direction of the particle is parallel to direction of the wave. Question 20. Which statement describe the waves? Yeah, D is the right answer. The waves both have the same loudness, same height, but they have different vibration or pitch. So D is the right answer. 21. The diagram represents waves from four source, which has a highest frequency. So number of vibration per second. For D, it's maximum. You can see the same question. Two students are measuring the speed of the sound. The students are provided with a starting pistol, a stopwatch, a measuring tape. A starting pistol, when fire, produces a loud sound and a puff of smoke. Describe how student could use apparatus to calculate speed. So that's the same thing. Finding the speed of the sound. This experiment. Stopwatch, starting pistol, measuring tape. So you have to write this whole procedure. Then a device at the bottom of, yes, you have to draw the diagram as well. A device at the bottom of a sea emits a sound of frequency 200 hertz. The speed of a sound in a sea water is 1500. Calculate the wavelength. So what will be the wavelength? The formula speed is equals to frequency multiplied by wavelength. So wavelength is speed divided by frequency. So 1500 divided by 200 equals 7.5 meters. In the next part, the sound wave passes from air, seawater, into air. So sound wave is traveling from water to air. The question is, state what happened, if anything, to the frequency. What happened to frequency? Frequency will not change. And this, what happened to speed? The speed will decrease. What is meant by ultrasound? Meaning of ultrasound, sound which is having a frequency more than 20,000 hertz, because like the audible from 20 to 20,000 we are able to detect, but the sound which we are not able to detect, or sound which is above the audible frequency, known as ultrasound. And what will be the frequency? The minimum possible frequency, like it will be 20,000 hertz, or more than, you can take any value. 20 minimum is like 20 because it started with 20 and so on. Or 20 kilohertz you can also write or mention. electromagnetic, which of these waves are electromagnetic? Like their radio waves are there, ultrasound and visible. Electromagnetic means a wave which can travel through vacuum. So radio waves and light waves are both electromagnetic. And longitudinal, sound, ultrasound, sound or ultrasound, these are longitudinal. Ultrasound passes through the both human flesh and the bone. The ultrasound source sending a wave into a human flesh. The ultrasound wave travel to a point X and then passes through a thickness and reflected back to X. Means what happened? Like the sound travel and then it bounce back. The total time taken by the sound to travel in the bone from X to Y is 9 exponent minus 6 second, means 9 microsecond. The speed of the sound in the bone is 4100. Calculate the thickness. So what is the thickness? Speed is equals to 2d. So in this case, it will be twice the thickness, the d, divided by t. Or you need distance. The thickness is a distance here. So speed multiplied by time divided by 2. So speed is given 4100. Time is there 9 exponent minus 6 divided by 2. You will get the thickness of the bone. Is it clear how to do this question? So 0.0185 meter. Then state what is meant by frequency, number of vibration in 1 second known as frequency. The sound wave travel in air through a barrier, a small gap. Figure 7.1 represent a compression of a wave traveling towards the barrier. What is meant by compression? Region of high pressure. The wavelength of a gap is smaller than the width of the gap is smaller than the wavelength. So it's a smaller gap. So draw a pattern. What we'll draw? We'll draw maximum diffraction will occur, curve. A barrier is adjusted so the gap become wider. Describe how it affects the pattern. So less diffraction, the sound will spread out less. The frequency of a sound is 6800. The speed is given, you need a wavelength, so V is equals to F lambda. Then state a typical value of a speed of a sound in liquid. What's the speed of sound in liquid? Typical value. So 1500 meter per second. So these are the questions related to topic sound. We completed this. I will share the weekly homework as well related to this. Any question?